Hi and welcome to this video for the BTEC Applied Science Level 3, Unit 19, where we're going to be looking at calculating empirical molecular formulae as part of using the mass spec information. So as part of the assignment, you'll be given some percentage elemental compositions, a mass spec, and just need to perform the calculations to determine these formulae. So we'll work through this together, calculators in hand, to see how it's done. Now, first off, percent you can basically just treat as grams. So in the same way in previous units, you worked out the number of moles of a substance by doing mass over relative atomic mass when you're dealing with the elements. We'll be doing the same here. So 58.8 divided by 12, 9.8 divided by 1, and 31.4 divided by 16. And 16. Now, once we've got the moles, we want the simplest ratio. 1.8. We want the simplest ratio between them. So we want whole number values, integers, 1 to something or 2 to something, as it might end up as. So the way we get that is whichever one of these three values is the lowest, you divide them all by the lowest value. So it's obviously down here, the 1.9625, we divide by itself. You'll always get a value of 1 somewhere because any number divided by itself. Okay, so as you can see, we're still not at integer values for each of them. It's quite rare that you will actually get 3 whole numbers from this unless the question's been set up particularly nicely. What we can do is a little bit of rounding off. So if your number is very close to a whole number value, i.e. the 4.99, or if you had, say, 3.01 or something, we can just round that off. 1, 1, 4.99, we can say it's just 5. Now 2.497, that's quite far away from a whole number. Cutting that off to 2 or increasing it to 3 is quite a large percentage change. 2.497 you can see is fairly close to 2.5. Now 0.5 is a common fraction. You should be aware of your common fractions: quarters, thirds, halves, 3/4, 2/3, even less common ones, sort of like 8ths and such. And when we've got a common fraction like that, so I'll put this as 2.5, what we can do is a little bit of scaling of this ratio so that we get whole numbers. So with a half, the easiest way to turn it into a whole number is just to double it. We double the 2.5 to 5. We would therefore have to double everything else to keep the same ratio. 5 becomes 10 and 1 becomes 2. So you don't always need to do this. If this came out as 2.99, for example, I could have just rounded it off to 3, and 351 we would have been done. But if you've got these common fractions that are quite far away from a whole number, then you will need to keep the ratio but scale up to get whole numbers. So this is my empirical formula. And that's that done. Now, to get the molecular formula, what we need to do is look at the mass spec. We find the molecular ion, so we can see here, and this will tell us the molecular mass, 102. So the peak furthest to the right doesn't necessarily need to be the tallest, so some people confuse biggest with the percentage abundance. It's the highest mass over charge value you're looking at. Disregarding any tiny carbon-13 peaks or such, sometimes pop up to the right. And what we do the molecular mass divided by the empirical mass. 102 there. Working this out, we've got 12 times 5, because carbon, 12, 5 of them, plus 1 times 10 from the 10 hydrogens, plus 16 for the oxygen times 2 of them. Add that up, 60, 70, 32, 102, under there. So this equals 1. What it's telling us is the empirical is the same as the molecular, because we would do 5 times 1, 10 times 1, and 2 times 1. Now, if this mass spec, say, was a bit bigger and it had a peak at 204, for example, and 204 divided by 102 was 2, then these three numbers here, it's telling us to multiply each of them by 2. So we do 5 times 2 is 10, 10 times 2 is 20, and 2 times 2 is 4 to get C10H20O4. But, like I said, in this case, just 1. So our molecular formula is that. And then we can go on and use the other specs, the proton NMR and such, to figure out exactly how those pieces are put together. And that's it for this. Thank you.